Have you ever looked up at the stars and wondered how many other civilizations might be out there? How many planets might hold life or perhaps even intelligent beings, asking the same question about us? To explore this mystery, scientists use something known as the Drake equation, a formula that doesn't give an exact answer, but helps us estimate how many civilizations could exist in our galaxy, the Milky Way. The Drake equation was created by astronomer Dr. Frank Drake in 1961. It was never meant to be a proven or experimental formula. It's theoretical and educated guess, designed to help scientists think about all the steps that must happen for life to appear and communicate. In short, it's a mathematical framework for one of humanity's oldest questions. Are we alone? The equation looks like this. N equals R star times Fp times Ne times Fl times Fi times Fc times L. Each term in this formula represents one stage in the chain that leads from stars to planets, to life, to intelligent communication. Let's go through each term and see what they really mean. The first one, R star, stands for the rate of star formation. How many new stars are formed in our galaxy each year? Astronomers estimate that the Milky Way creates around 1 or 2 new stars every year. That means every single year, there are 1 or 2 fresh chances for new planets. And maybe for new life. For our example, we'll take our star equals 1. Next, we multiply by Fp, which represents the fraction of those stars that have planets. Decades ago, we had no idea how common planets were. But today, thanks to telescopes like Kepler and TESS, we know that planets are everywhere. Almost every star has at least one. So, we'll assume Fp equals 1, meaning nearly every star in the Milky Way has its own planets. Now comes Ne, the average number of planets per star that could support life. This depends on the habitable zone, the distance from the star where it's not too hot or too cold for liquid water to exist. For our Sun, Earth lies perfectly in this zone. Based on current data, scientists estimate that roughly 1 planet per system could be habitable. So let's take Ne equals 1 as well. The next term, Fl, is where things get mysterious. It represents the fraction of those habitable planets where life actually begins. Just because a planet could support life doesn't mean it will. Life needs chemistry, stability, and time, and even then, it might never appear. Here, our only example is Earth. We don't yet know if life began easily here or if we were just incredibly lucky. For our example, we'll take Fl equals 0.33, meaning that maybe 1 out of 3 habitable planets actually develop life. Next comes Fi, the fraction of life-bearing planets where intelligent life evolves. Life doesn't always mean intelligence. Microbes or plants could fill a planet without ever developing reasoning or technology. On Earth, it took billions of years for intelligent beings like humans to evolve. So, scientists often assume Fi equals 0.01. 1 in 100 life-bearing planets give rise to intelligence. Then comes Fc, the fraction of intelligent civilizations that develop technology and begin communicating. Not all intelligent species might build machines or send radio waves. Some may stay peaceful and primitive. Others might destroy themselves before ever reaching the stars. Let's take Fc equals 0.1, meaning only 1 in 10 intelligent civilizations become detectable through signals or communication. Finally, there's L, the average lifetime of a communicating civilization, how long such a society can send out signals before it disappears. This is one of the most uncertain parts of the whole equation. Civilizations might last only a few hundred years before destroying themselves, or they might survive for millions. The longer they last, the higher the chance that 2 civilizations exist at the same time to communicate. For our example, we'll take L equals 10,000 years. Now, let's put all these numbers together. 1 times 1 times 1 times 0.33 times 0.01 times 0.1 times 10,000 equals around 3.3. So, according to this theoretical calculation, there might be about 3 communicating civilizations in our entire Milky Way galaxy. maybe humans, and 2 others somewhere out there among hundreds of billions of stars. But remember, this result is not an answer. It's just an educated guess. The Drake equation doesn't predict. It only helps us think. Each value in the equation is filled with uncertainty. Some scientists believe the number could be thousands of civilizations, while others think it could be just one. In 2024, a scientist named Łukasz Lamza published a research paper titled Chemical Complexity and Prevalence of Life in the Universe on ar14.org. He used new chemical and planetary data to estimate how often life could arise. His results showed that the number of life-bearing worlds could be as low as 1 or 2 per galaxy, or as high as 13,000. That huge range proves just how theoretical the Drake equation really is, a framework for thinking, not a final count. And yet, despite being uncertain, the equation changed the way humanity looks at the cosmos. It reminds us that life depends on a delicate chain of chances: stars, planets, chemistry, time, and survival. Somewhere in those billions of stars, another civilization might exist right now. Maybe they're sending out a signal just like us, hoping that someone out there is listening. The Drake equation may be theoretical, but it captures one of humanity's greatest dreams: the dream that we are not alone. And until the day we find that first signal, it will continue to inspire scientists, dreamers, and explorers to keep looking into the dark, wondering who else might be sharing this vast universe with us.